So last year, we were presented with some statements that Alexei had to say. If you guys remember many of these, he was basically talking about release schedule and the release plan. So as you guys have seen, there have been a few changes. This is a good thing. I think we should all be very thankful for these. But it also kind of gives us a chance to have a little bit of fun and smile and laugh, if you will. So we basically talked about eating an Ubuntu hat. Come on, seriously. So that was the first hat that he said he was going to eat if he couldn't do a release on time. Oh darn, he ate another one. And then finally he decided that okay, 3's enough. So but the problem is these are not real. So what I decided to do back in the US was make sure that next time Alexei wished to actually eat a hat, that he would have a real one to actually eat. So Alexei? Other way, backwards. So there we go. Alrighty. So let's just dive into this and have some more fun. Hey, how about if I start at the beginning instead? We can always do it differently. Cool. So we're going to basically talk about performance tuning Red Hat Enterprise Linux using Zabbix to basically identify your problems. What we're going to talk about, a little overview. We're going to dive into some interesting topics. One of them is Little's Law, which is actually kind of a math formula, if you will, or basically a principle that defines performance tuning in general. We talk about a little bit of instrumentation of how you actually dive into what you're looking at. Many of us are used to looking at Zabbix screens, but let's take a look at maybe some other ways to figure out what's going inside the kernel and stuff like that. And we'll finish with a simple real-world example that with some simple before and after tuning examples. So who am I? My name is Andrew Nelson. I am a consultant with Red Hat. I've been with Red Hat over 2 years now in North America. I basically spend about 100% of my time on the road. Meaning every Thursday I will leave the client site, come home, spend a weekend, then Sunday I'm back at the client for the following week. It's been a great time. Red Hat's been a lot of fun to work with, so I've been enjoying it. But I've also been involved in the Zabbix community for almost 8 years now. It's been a while. I think I started in one of your early 1.0 releases many years ago with a client that was running it, and my boss basically said, hey, why don't you manage this Zabbix thing? Okay, fine. Little did I know where it would go. So if you see me in the forums, I go under the name Nelson AB, also same as in IRC. I also have written 2 projects that are related to Zabbix. ZabCon, the Zabbix console was kind of the naming for it, and the ZBX API, which is a Ruby gem for interfacing with the API. So Ruby is kind of the language that I prefer to work in. But anyone who wishes to help, please make yourself known. So tuning, why do we tune? We've all done it at some point. We've all had a need to do it. There's various reasons for doing tuning. Hey, the system's too slow, we're going to upgrade the hardware, or we don't have the budget for a hardware upgrade, so we've got to make this legacy, 286 computer scream as best we can. And, sometimes you try and you try, or, hey, there's always the lovely one, it's too slow. Users, what the heck, they're always so freaking specific, But bottom line, it is to increase your return on investment of whatever equipment that you've got in some way, shape, or form. That's kind of the bottom line of all performance tuning. So Little's Law, like I said, we're going to dive into something kind of interesting. Little's Law is basically, it was published in 1961, and it was essentially a restatement of the Erlang formula. Erlang was a mathematician, if I'm remembering correctly. Around the turn of the century, he published a series of mathematical equations that basically defined telephone networks and call queuing and call congestion and so forth related to telephone networks. Little came along in the 60s, and he actually described this more in terms of banking, in terms of people walking into a bank to stand at a teller and have an interaction with a teller. And it's a very simple formula. The length of the queue is equal to the number of customers walking in times the time that it takes to service that customer. So if it takes, 10 minutes to serve a customer, and you've got one customer every 10 minutes, and you've waited 10 minutes, your queue should be one customer long. So those are kind of the things. Some of the pieces you can fix, you can change in here. Some of them you cannot do. But hey, what happens if we start modifying some of these variables? If we assume that L is essentially our queue depth, and we were to increase queue depth, what can we do? Hey, we can service more items, but our latency is going to increase. So latency is very important when you're dealing in networks and disk I/O and stuff like that. You want to have low latency networks, but you also have to buffer. So how do you do your buffering? And this also kind of describes another problem that's very common, and that's buffer bloat, where your buffers get too large because you're trying to improve performance. However, you end up getting worse performance, which is kind of an interesting sub-problem, if you will. Lambda is the people coming in. Lambda you often can't change. Lambda is often what your users are doing, as we describe in the next one here. So, as we're saying, so Lambda, like I say, you often can't control the arrival rate of information. Now, if you were to look at it from a whole systems perspective that is made up of many different smaller components, sure, you may be able to tune those individual components and how they interact with each other. So from that perspective, yes, you can tune Lambda. You can tune the time that it takes to service each request on a smaller scale. But we're not going to really talk about that one too much today, because it's a harder one to quantify. It's a really difficult one to discuss. But instead, most often, what do? We're going to be doing the queue length, which is our buffers. And we're also going to be, changing time to service a request, which, like I say, is kind of, arrival rate at the macro scale, but at the, the micro scale, but the macro scale, it's the, time to service, which is often disks, networks, and things like that we can speed up. So how do we instrument? Many of us are already used to using the tools that are built into Zabbix for instrumentation. We're used to understanding the file.vfs and the various other pieces built into the agent. However, there's many tools that are out there. And in the many mailing lists inside of Red Hat, especially when we have a mailing list internally, it's a technical list where literally a solutions architect who's kind of associated with kind of a pre-sales type environment will post a question up and say, hey, I've got a customer that's got a problem with this. How do we figure out what's going on? And they will often talk about diving deep into the details of, okay, here's what you're going to look at. Here's where you're going to pull this piece of data and so forth. So system tap is one of the things I'll talk about. SAR is a common program that we use inside of Red Hat. SAR, unfortunately, doesn't do too well with Zabbix. But SAR will generate a whole bunch of I/O statistics on the local host and so forth. But most of your data and most of the tools that you use, like netstat, socketstat, SS, and so forth, actually pull their data from two sources, /proc/sys. That is where you can pull almost every single piece of tuning information you need to know in terms of instrumentation. If you really need to get down and dirty and really get to see some really interesting pieces of data, then you're going to use something like System Tap. System Tap is akin to dtrace in the Solaris world, but the beauty of System Tap is you can tap a function in the Linux kernel, pull information out of that function, and maybe even alter how that function operates. You can compile it on one server in the back end because you have to have the debug kernel installed along with the development libraries installed on the host. Once you compile that system tap module, you can take it to a production machine that does not have the debug kernel installed, does not have a development library installed, and you can run that system tap module on that production system. The only requirement is that the kernels are the same version. So it's actually pretty cool. Last year, this was actually something I posted up in the forums, kind of sharing with people about something you could do. The script was a little large to show you guys today, with the screen real estate available. But the key thing about it was it would check inside every time a I/O request was done on the network. Anytime any process decided to send a packet of information received or sent on the network, I would basically catalog what the process name was and keep it. So if the process quit, it stayed in this table. Now, as you can see, the interesting thing is oftentimes you'll be on a system and you're going, wow, what program is eating up my bandwidth? Well, with a tool like this, with System Tap, you can actually now look and see, aha, in this case, it's my swapper program that's actually doing a lot of data. Why the hell is swapper on the network? So maybe I'm going to dig deeper. Or, hey, some users on the system running Firefox, why are they doing this on an admin system? First off, we'd probably see that in the process table, but we may not think that Firefox is really transferring much data until we start to look into something like this. So System Tap is a very powerful tool that we can use to instrument a lot of this stuff. So where do we find more information? That's always an important thing. The kernel documentation is always going to be the best source of information. Go to the source is kind of a common mantra that you'll hear from people. So the kernel documentation RPM will basically install in user share doc, kernel doc, documentation, and then it's a series of directories inside there and a bunch of text files that dive deep into the information. If you want to know what a specific kernel parameter in the sysctl conf file is, that's the best place to look it up. And it will intimately describe a lot of those, and it's a great place to go. The Red Hat 6 Performance Tuning Guide, which is part of our external documentation that's freely available, is also another really good source. I have a confession to make. Before I came to Red Hat, I didn't really think that much of what Red Hat did was too special. Having been there for 2 years now and actually read a lot of the stuff that we write, produce, and make available for free, the quality is actually pretty amazing. And a lot of it, the thing I enjoy the most out of it is there's not much fluff, there's not much opinion in what's written. It's here's the problem, here's how to fix it, or here's the problem, here's what's involved, here's your solution, next. And it's very straightforward in terms of reading. So that's one thing I've actually found to be kind of a surprise for me, and it was something I didn't expect, but I've very much enjoyed. Our documentation also for RHEL 6 is, like I say, equally in depth. So if you can't understand it in, say, like the kernel docs, go into some of our other documentation that we've got. The Red Hat knowledge base, I like to call this the secret sauce. The knowledge base is available to any customer who has a Red Hat subscription. In there you will basically find specific K-base articles describing many issues that that customers have had and how to tune or fix appropriately for them. There's also a performance tuning class that Red Hat does that is 1 week long that describes a lot of this in detail, going into disk tuning and so forth and so on. And it was during this performance tuning class that I actually discovered System Tap, thought about it, and said, this is something useful for Zabbix as well. And that's when I created the Zabbix stuff. So I'm probably boring you guys to death, so let's get into some interesting things. Let's maybe start looking at some graphs and start seeing some real data. So in this hypothetical situation, user comes to you and says, hey, we're seeing some performance issues on our network running NFS transfers. This is what our network looks like. So this is a very simplistic network that I basically have for testing 2 systems, both running RHEL 6. software RAID of 256 gig drives, and then 8 gig of memory with a quad-core processor per machine. These are decent little, desktop boxes that are being used straight into a gigabit switch, straight with a Zabbix proxy tied into the whole thing, and then going across the WAN back to my main Zabbix server. So, so the user comes to you and says, hey, we got some problems. So you derive a simple test case. Now that's a key thing with any performance tuning is you need to have a well-defined test case. So my test case was I had a 10 gigabyte file filled with random data that was pulled from dev urandom. So I generated a 10 gig file that's completely random, so that way I don't have, I can minimize the chance that cache will actually be able to optimize some of this data. In addition, so the first thing we do is I will clear caches on both ends, on the server and on the client. Then I will transfer the file using DD from the client to the server. All actions are done from the client system as well. And then we go pulling it from the server back down to the client, and then we basically take it from the server and essentially copy it to another file on the server as well. So, but we're doing this from the client. So this is kind of an interesting one because this exercises your network in both directions. Due to the nature of a lot of this, it turns out there wasn't much I could do in the disk area, and I'll get into that later. So, graphs, we like to look at those, right? So here's what we're looking at. All right, these are all pretty standard that we're fairly used to seeing. So this doesn't tell us very much, right? All right, so bandwidth is peaking at 76 megabytes a second. All right, so we're basically taking up a lot of memory cache. So the kernel is caching our data. Okay, I/O wait state. We're not really sitting too much time in I/O wait. We're a quad-core processor system. That looks to be about 1/4. So it looks like one of our cores is really filled, sitting in I/O wait. Anyone see anything that just screams at them and says, hey, here's a performance bottleneck? Yeah, it's not really in there. So let's add some more graphs. So let's start looking at some more interesting details. So here we're going to look at TCP queue depths. We're looking at the network driver layer essentially, and we're saying how much data is waiting to be transmitted by the TCP stack. How much data is received waiting to be operated on by the TCP stack. And so we're looking at this. And these are kind of an interesting one. I'll talk about that in a second. They're kind of a little misleading, but they kind of show some other things that are really interesting going on under the covers. Let's see. NFS retransmits. NFS retransmits is actually a really useful one for NFS. The tuning that was initially done on the system, this was a system that was basically put into a state of poor performance. Done so that I could show a lot of these kinds of steps. Does anyone see a problem with that? Okay, so anytime you retransmit data, you've basically doubled your time to operate on that data. You want to always reduce the number of retransmissions of any kind of data whenever possible. So, but how do you know you've got to retransmit unless you can document it? And so that was kind of a useful one. Last one, we're looking at TCP retransmissions. Turns out that one's actually kind of a red herring in a way, and I'll just talk about that in a minute. So this one doesn't quite show what you think it does, or doesn't quite work as well. In the slide, basically I've got the programs that were used to generate each one of these graphs. So essentially for retransmissions, basically I'm having to look at, there's a special shell script I wrote that basically pulls data out of /proc, depending on which file you want to pull it out of. And NFS retransmits is straight out of, /proc net RPC NFS, and we're basically just going after the RPC line and then pulling column 3 out of it. So let's see, TCP queues, the queue depths, This is using a program called SS, which is socket status. So we're pulling socket status, which tells us the status of every socket on the system in use. Then we are basically pulling out a specific column of socket information. We are then adding all that data together to get a final result of, how much memory is in use by all sockets on the system. So forth. So, disk operations. Disk is another good one to start looking at too. What's our I/O ops like on the disks? Which disk is being used the most? This is a RAID system, so you'd expect to see fairly even on both systems, which we're seeing. We're looking at, once again, we're looking at the before information. Once again, we're looking a little deeper. This would be, this is a very useful one because we're looking at read merges and write merges. And this is tied in with the I/O scheduler of the, within the kernel, because it's trying to optimize reads and writes according to where the read head is over the spindle based on the information that's coming in. So if I'm on track 2 and I've got a piece of data that's for track 2, and let's say 2 milliseconds later I have another piece of data for track 2, it's going to try and write that piece of data for track 2 before anything else with write merging. So write merging is very common. You'll see that actually in the CFQ scheduler, the deadline scheduler, but you won't find it in like the no-op scheduler. So no-op doesn't try and do any merging whatsoever. It just basically takes it and dumps it. No-op turns out not always the best in this situation. No-op scheduler is the best scheduler to use if you've got flash drives or if you've got hardware RAID. Let your kernel push it off to that piece of hardware, let it spend as little time handling that I/O, send it to the hardware, send it to the I/O device, and let it handle it. Same goes if you've got a SAN storage device. Use the no-op scheduler on your SAN storage and push it off. Also, same goes with virtualization guests. If you're in virtualized environments, do not have a I/O scheduler on the guest. Use the no-op scheduler. Let the hypervisor handle all I/O operations for you. So, little slight divergence there, but so let's change some information here. All these are stored in the etc sysctl conf file. When you make a change to this file, you will then run sysctl -p. That will basically reload it and change all of these kernel parameters. Alternatively, you could do an echo into one of the many proc files that are out there. So we're going to change the memory in bytes available per socket. So this is a memory available per socket to our connections. We're going to go from about 132 kilobytes to 10 megabytes. So we've expanded out that buffer, if you will, that we can receive. Remember I was talking earlier, as we increase our buffer, we increase latency. So this could have some problems. So we need to be careful of making this not too large. You go out and read many blogs and you'll see people will talk about taking these numbers and just exponentially increasing them. Hey, we've got 8 gig of memory on this system, why don't we make this 4 gig? I did it, it doesn't work. So default sockets, buffer size in bytes. This is the default that gets created in terms of allocated storage whenever a connection initiates. So if I start a connection to a host, that host is going to automatically have 8 kilobytes of memory pre-allocated for storage and for receiving, both in receive and transmit, which is what these two are. So WMM is transmit, RMM is receive. Moving on, a couple others. This is a tuple. It's a very interesting one, because it's kind of hard to understand. This is also a very misleading one. Anyone see what's kind of different about this? So, 343,104. That's not very many bytes until we realize, oh wait, I'm talking page sizes. Page sizes in the Linux kernel is 4 kilobytes. So you'll all start to notice a very common theme. Everything's powers of 2, usually in 4 kilobyte increments. You want to make sure that your buffers are bounded appropriately. So you don't want to have a 4 kilobyte disk buffer, but you're going to write 6 kilobytes of data. You want to write 8 kilobytes of data to a 4 kilobyte disk buffer, and those kinds of things. You want to make sure that your common denominator is even, if you will. So we're basically setting up, this is how many pages are available to the stack in general for TCP memory. So this is available in general for all connections. Then this is a per TCP connection, and this is per bytes. So remember I was talking about how different they are, that, hey, this is in pages, this is in bytes. I think if I remember correctly, I set this to about 20 megabytes. And this is 10 megabytes, as we remember. And notice how this number right here is the same as what we're talking about here. So we're basically setting, hey, socket size we're allowing 10 megabytes, and TCP sockets we're allowing 10 megabytes. This number is also kind of interesting because that's basically says, hey, once we start to get to that number in terms of memory allocation, then we're going to start to figure out ways to clear memory and a few things like that. So you want to make sure this is set in an appropriate level, maybe not the same as you'll see in many blog posts. And I've actually found that setting it to be the same as your top end doesn't work. So I've got it set to 80%, and I actually found that to be pretty decent. A couple other things, and then I'll get back into some more graphs and show you the final results. So FS tab is where we define how NFS is tuned. All NFS tuning is essentially done by the client. The client is the one who determines how big our data, our packet sizes are going to be. The client determines how quickly we time out and everything else. So as we can see, I had my timeout originally set to 1. Is that 1 second? That's 1/10 of a second. TCP time or NFS timeout values are in tenths of a second. Hence now I've got it to 150, which is 15 seconds. So if my I/O operation takes more than 15 seconds, then it will retry the NFS operation. Can you guys see how that would actually make a huge difference in performance? So that's kind of a useful one. Another one, this is something that I highly recommend that everyone have a look at and do. If you're using NFS, you're probably using NFS hard mounts. NFS hard mounts, if the NFS server goes away and the client is in the middle of an I/O operation, anyone had that happen? How many times do you have to pretty much reboot the machine? You have to wait for either the server to come back or reboot the machine, essentially. There are some ways to get around it, but if you add the INTR option, now you can interrupt the I/O request when your timeout occurs. So if your timeout is set to 60 seconds and you hit Control-C, you're going to wait 60 seconds for your timeout before you can kill your I/O operation. So like I say, this option can save you much anguish. So I did these changes. Here's what I saw in my performance change. I'd say that's pretty decent. So in terms of the client server, we went from 37 megabytes a second to almost 46 megabytes a second. When I went server to client, pulling it down, I'm seeing a huge change. Anyone have an idea why? It was kind of an interesting revelation as to why we see this change. Anyone got an idea? So when we do a write operation, we have to wait for confirmation. Well, networks have delay. So we're waiting for the delay of the NFS server to say, I've written the data, now come back. Whereas if I'm pulling from the server and I'm writing to my local disk, my delay is the local computer. So it's much, much faster. In addition, when I went from client for server to server via client, I'm exercising both directions of my network pipe at the same time. And so, my performance is much lower. Synchronous network does help with this, which this is a standard switch network, but there are still many other overheads involved, especially when it comes to ACKs and so forth. We can do some optimizations within the TCP stack as well. Maybe we can improve those numbers further. So before and after. As we can see, processor load decreased in the time. We can also note that time has decreased because we can look at the sizing of the graph. So we can also see that I/O weight didn't really change too much. Now, if we had just these graphs, would we really have been able to be overly effective in our tuning? Probably not terribly. Same goes with this. These are the same graphs that we're also used to. Okay, so we see a much narrower, more direct image or appearance in the graph, if you will. Higher bandwidths. Caching doesn't really tell us too much in that one either. But let's look at queue depths. So if we see our queue depths over here is about 2 megabytes in the TCP queues. So we're waiting about 2 megabytes of data, whereas over here we're kind of holding a whole lot more data in the buffer ready to be sent. So we're basically not spending time waiting. We're stuffing that buffer, and that buffer is just going to keep pulling data out as fast as it can. One thing to note, you'll actually see it'll peak up first, it'll spike, and it'll drop down, and then it will come back again later. And what I've observed is that is essentially the TCP layer figuring out or essentially settling into a normal for its TCP window sizing and everything else. So it's basically optimizing itself for that transmission as well. And so you'll see that settle in and then become a standard pattern. NFS retransmits. We went from up to, what was this, about 60? Yeah, about 45 maximum, down to 1. And that was a huge, huge difference. NFS retransmits. This was kind of, like I say, the red herring and everything that was surprising. I went from, what was it, 300 TCP retransmits to 1,000. I didn't expect that, to be honest. Best I can figure is because our buffer is now stuffed, as we can see, we're now stuffing our buffers completely. The other end is saying, hey, don't send me any more data, I'm not ready. Don't send me any more data, I'm not ready. Okay, send me some data, and now we're doing the retransmit. But because our buffers, our sizing is much bigger, we're going to see more TCP retransmit, information. So, disk I/O, once again, kind of a useful one. Let's see if I remember, that's about 20,000. Yeah, it's about 20,000, and yeah, just over 20,000. So our disk I/O actually improved as well, which would be expected because NFS is accepting that I/O at a much faster rate. We don't really see any changes here because we didn't really do too much disk tuning, so we didn't see any of that. So in quick review, we performance tune most often to increase our return on investment. Old hardware that we have to extend the life of, or customers who are complaining it's just too slow. Once again, why are they so specific? So Little's law is pretty much the law that defines and governs most of our performance tuning. And we need to be considerate of it. So it's essentially the queue depth is equal to the arrival rate time multiplied by the time to service. We can often change our queue depth, which is our buffering, and we can often alter to some extent our time to service, which is faster networks, faster disks, faster processor, faster memory, or more efficient I/O schedulers, and so forth. System tap, as I showed earlier, is a good tool to enhance and add more information to your performance monitoring. Documentation. Read the source. I know we'd all love to be able to do that sometimes, but the documentation that's out there is great. The kernel docs it should always be your first place to start when trying to understand how to tune your Linux kernel. To Red Hat subscribers that are out there, I encourage you to use the knowledge base. It is the secret sauce. I didn't know about it until I came to Red Hat. I love it now that I'm there. I use it a lot when I've got customers asking me questions and I don't know the answer. First place I go is the knowledge base. And oftentimes we'll find an answer in there. Also, as many of you guys have known, have a defined process for how you do your tuning. As you see, I created a simple script that basically was a very repeatable process. and I could repeat this process over and over and over. You need to have a repeatable process to do proper performance tuning, because you need to be able to document what you've changed and what your performance was before and after, as you saw in here. So that's another key point as well. And like I say, keep track of what your variables changed were. If you're using a version control system, say like Puppet, or sorry, a configuration management system like Puppet, that's a good thing to use, because Puppet has revisioning. Or if you're using a older school method of RCS in your Etsy file, directory to keep copies of these various files, great. Or Subversion in a central repo, or Git, whatever. At least this way you've got versioning and you can see what you've changed over time. So that's it.